Section 3. Section 3 shall cover sampling distribution of the mean and hypothesis testing. So let's move on to sampling distribution of the mean. So random samples rarely exactly represent the underlying population. We rely on sampling distributions to give us a better idea whether the sample we have observed represents a common or a rare outcome. So common outcomes are within 2 standard deviation plus 2 standard deviation and minus 2 standard deviation. So these are common. So if it's above 2 standard deviation from the mean, they become rare outcomes on both ends. So you can see this, like we try to demonstrate, this area represents about 95%, like what we discussed earlier. And if it's 1 standard deviation, it's represents about 68%. That's what we discussed earlier. The mean of the sampling distribution always equals the mean of the population. So it means if we have 5 samples we've taken, the mean of those 5 samples is always equal to the mean of the population. The sampling distribution of the mean is the probability that the distribution of means. So it means what we are saying, let's say this is the population of South Africa, and we take samples in different towns. Let's say 5 samples from 5 towns like this. So now these are 5 samples with 5 means. So if we have the mean of these means, it will give us the mean of the population. So that's what we're saying. Sampling distribution of the mean is the probability distribution of means for all random sample of a given size from some population. So in this case, we took South Africa and we took different towns. So these samples can have different sample sizes, but now their means, when we take the mean of their means, it means like we're saying, let's say x bar is like the mean of the population. We say over 5, so we say mean 1 sample 1, mean of sample 2 plus mean of sample 3 plus mean of sample 4 x bar 4 plus mean of sample plus mean of sample 5 divided by 5. So that's why what we are basically saying, we are saying we are getting the mean of the means, which are the mean of sample 1, 2, 3, 4, 5. When you get the mean of the mean, we are averaging those means to get the population mean. So that's what we are saying. Sampling distribution of the mean is the distribution of the means for all possible random sample of a given size from some population. By taking a sample from a population, we don't know whether the sample reflects the population of the mean. So for example, if we take one sample, let's say sample 1, if we only take one sample, we are not actually sure whether that same one sample represents the total population. So by taking several samples from the population, we increase our chances of getting a better result. So we are saying by taking a sample from population, we don't know whether this sample mean reflects the population mean. From sampling distribution, we can calculate the possibility of a particular sample mean. The chances that our observed sample mean originates from the middle of the true sampling distribution. So what we are dealing in sampling distribution of the mean, we are actually given the probability of the sample mean being the actual mean of the population. Because remember, a sample is supposed to represent the total population. So in sampling distribution of mean, we are getting the possibility or the probability of that particular sample that we have taken, that it actually represents the representativeness of that sample. So it's basically gauging how accurate is our sample. So sampling distribution of mean is a mean and a standard deviation, just like any other normal distribution. So now the difference now, remember, for the normal, we said x follows a normal distribution of mean mu and variance some sigma squared. But for sampling distribution mean, it is x follows a normal distribution with mu. But now the difference now is the sigma squared divided by n. That is the variance. So when you get the standard deviation, it will be SD, standard deviation, it will be sigma over square root of n. That is the standard error. Let's move on to the next. So standard error of the mean measures the variability in the sampling distribution. Roughly represents average amount the sample means deviate from the mean of the sampling distribution. So this is what we discussed. Now, for the sampling distribution of mean, this is your standard deviation. So remember, you divide by square root of the number of samples. So the sample size n, remember, there is a different distribution for each different sample size. So, like the example we gave for South Africa, you take 5 samples. So we are saying these sample sizes have a different sample, different distribution. So let's say this is 2 million, 3 million, 1 million, 3.5 million, 5 million. So because they have a different sample sizes, they have different distributions, so their means can also be different. So that's why we are sampling whether their means, how accurate or how close are they from the population mean. So just remember the important part, that you divide by square root of n, which is number of samples. So these types of theory can only be understood by doing some problems. So let's move on to example 1. Suppose you measure the heights of 100 randomly sampled women from a key point 100 randomly sampled women from a population that has a mean of, this is the population mean, the standard deviation 2.5. For what mean height will 5% of the heights fall above? So another keyword, fall above. So we are looking for a greater above. So basically what we are saying, we've got our n, so it's 100, our nu is equals to 64 inches. Then we've got our standard deviation of the population, 2.5. So when you draw our graph, we want to know 5% of above. So it means we are looking at this area. So let's shade it. This area should be 5%. So this is the area. So we are not interested in this one. We want this one, which is above. So now for us to get this 5% from the tables, the tables 5% is 0.05. That's 5%. So we look for 0.05 on the proportions so that we can get the Z score here, which we currently do not know. Once you know the Z score, we will be able to use the formula. Remember, x is equal to, Z is equal to x minus mu divided by sigma square root of n. So n we have, standard deviation we have, mu we have, z we determine from here, then we will have it when we want to determine it from the tables, then we are left with x. So x is the mean height that we are looking for. So by mean height, what we are looking for. So let's move on. Solution. So we need first to find Z score from which 5% of the area under the standard normal distribution lies above. So this is your 5%, your 0.05 we've discussed above. So you're supposed to get about 1.64. Let's demonstrate it. So you go to your tables and look for. So you see now, these tables, they remember what I discussed about with you in the previous chapter, that you first look at the chart. So you need this data in this area represents the data from the Z2. So which means this is 95% and this is 5%. So now what we do is like we look for the so this data is representing the shaded region, which means we look for 95% in order for us to get this Z score, because we are mainly interested in the Z score, which divides this one into 5 and 95. So in this case, this graph only represents the shaded part, so it means we are looking for the 95. So 95% is 0.95. So from the tables, there are two digits which are close to 0.95. So there is this one which I have chosen and this one. These ones are the two which are closest to 0.95. But for you to get the accurate digit, if you have time, you can do the linear interpolation, which gives you something like 0.165 to do the linear interpolation. But for this example, I was just trying to illustrate it so that I don't make the problem too long for you guys. So now, to convert this distribution of means, we use the central limit theorem. With a sample size of 100, we can assume that the means will be normally distributed with a mean of 64 and the standard deviation of 2.5 divided by 100. So this one is 2.5 is n over standard deviation over square root of n. So your standard deviation is 2.5 square root of n square root of 100, which gives you 2.5. So remember, from this is determined from this one, say z is equals to, so that you don't wonder how these people are solving this thing. So x bar mean over mu over square root n over square root of n. So what we need is this one. So it means for us to determine this one, we multiply both sides by this, which means we take this one there, so it becomes z over square root of n is equals to x bar minus mu. Then from this, you put your, remember if it crosses the equal sign plus and cos, so it becomes mu plus z sigma over square root of n. So this is how we reach this point. So once you are here, you know your mu, you know your z value, you got in the previous slide, and you know your standard error. So once you do that, you get your x. So when you redraw it, you know that 64.41 is somewhere here. So we are looking for the mean height. So we can conclude that 5% of mean height will fall above a mean of 6.44 inches. So let's attempt. So first stage, you determine your normal distribution and you draw your graph like this and indicate the shaded area. Then from your set tables, you determine this value. But if you have time, you can use linear interpolation. You're supposed to get 1.645. Then from there, you use your set formula for the normal distribution of sampling means. Then you determine and rearrange and you come up with this one. I think it's simple enough. So let's move on to this second example. We have a distribution of IQ scores, which are normally distributed with a mean of 100 and a standard deviation of 15. When drawing 16 samples from the IQ distribution, what is the range of means that will cover the middle 95% of the means? So when talking about the middle, we're talking here. For middle, we need the middle section, which means we will share to become 2.5%. And this one will also become 2.5. Because we are looking at the middle, which means we are dividing this one will be 95%. So this is the region that we don't want. So now we want the middle 95%. So it means at both ends they will share the 5%. So it becomes 2.5 and 2.5%. So now we know our n, know our standard deviation, know our mean, and we know what we are. So now we need to determine the set score for here and here. So let's move on. So this time we work out the other way around by first finding z scores for which the standard deviation normal contains 95% in the middle score. So if you go to 95%, it means that we are dividing this one to 0.025, 0.025. So you can go, remember the normal distribution is symmetrical. That's why if you find 0.25 on this end or 0.25 in this end, it will be a negative, and on the other side is positive. So it will be just easier to determine this area because it's covered. So from Z tables, you know that the values that are represented here, they cover the left side. So in our case, you know that if you find Z value of 0. If you get the Z value here, it will cover this area. So we know that we can find a proportion of 0.25 from the table so that we can determine the Z score. And from this side, we know that in this side it will be this whole area. Since the graph is like this, it means that this whole area is, if we get the Z value for this area, it means if we leave 0.025, which means the shaded area will be 0.9750. So from the tables you can see that 0.975 is here. So you just determine the Z score. It's 1.96. So your Z score is 1.96. So it means since we want the middle score, it means our distribution will be here to be plus 1.96, and on this side to be maybe minus 1.96, something like this. So this one's will be we don't want, so the 95% will be this one. So now, since we got the Z scores, we can go back and you can see also that if you consider 0.25, you also get minus 96. Remember, the normal distribution is symmetrical. So once you know that the values will be identical, you just write it because they are symmetrical. But I just wanted to show you whether you start with that one or the other one is to get the same. So now that our graph, we redraw it like this, then we convert the Z scores to mean IQ scores, knowing that the standard area is equals to standard deviation divided by square root of n. Standard deviation is 15, square root of n, 16, square root of 16, so you get 3.5, 75, I mean. So this is your standard area. So now, for you to get the mean IQ score, will therefore be between these two. So now, remember there are two values here. So remember, we are always using this formula. So in this case, we have already rearranged it. Never forget this area, this formula which is always used for sampling distribution of mean. So what they just did here, they want to determine this one. So we rearrange to this. So once you rearranged, then you can input your values, your mean, your Z score, and your standard error. So now remember, you are doing it for both. So the other one it will be a negative and the other one it will be a positive. So let me demonstrate it. So here, if you rearrange it, it becomes x bar, like we have demonstrated. So it's equals to mu plus z square root of mu. So our mean is always 100. So remember our Z score now for the first one, it's negative. It's minus 1.95. So it becomes minus 1.95 times the standard error. So this one I've already determined it. What it is this one times 0.75. So once you do that, you get to this value. So for the second one is also using this formula. I want to again, so it's 100. So since the Z value here is positive, it's plus 196 times That's the point here, 2.75. Then you get this one. So now, therefore, for a sample size of 16, we can expect to obtain a mean IQ between 92.65 and 107.35 points percent of the time, 95% of the time. So it means between 92 and 6.5, 92.65 and 107.35 will give us a 95% chance. So remember the question was, when drawing 16 samples from the IQ distribution, what range? So it's a range of means that we cover the median 95%. So the range is 92.65 to 107.35. So this is the range. That's why we're saying it's between. So it's a range. So let's move on. Things to note. Researchers can increase the accuracy of an estimate of a population mean by increasing the sample size. In turn, reduces the standard error. What it means, remember, our standard error is standard deviation over square root of n. Let's say our standard deviation is 10 and our sample size is 25. So square root of 25 equals square root of 25 is 5. So 5 divided by 10 divided by 5 we get 2. Because our sample is 25. Let's say our sample increase it to 100. So it becomes 100 over 10 over square root of 100, which becomes 10 over 10 equals to 1. So that's why we're saying researchers can increase the accuracy of an estimate of a population mean by increasing the sample size. So if the sample size is increased from 25 to 100, you see that the standard error decreases by 1. So imagine if we increase our sample to 1000. So 1 square root of 1000. 110 divided by square root of 1000, square root of 1000 becomes, square root of 10,000, it becomes 100. Increase our sample, so you can see that it becomes 0.1. So you can see that when the sample size was 25, the standard error was 2. When the sample size was 100, the standard error was 1. When the sample size was 10,000, the standard error was 0.1. So as the n increases, we see also that the standard error decreases. So that's what we mean by researchers can increase the accuracy of an estimate of the population mean by increasing the sample size, which in turn reduces the standard error. Practice question for sample distribution of means. So we've got about 4 questions for you to practice, question 13 to question 16. So you can attempt to work out these ones, and if you have a problem in solving them, you can contact me on this number so that I can help you. But let's just discuss the general. Question 13. Suppose you draw 24 samples from a population mean with 63 and the standard deviation of so this is the sample size n, the mean mu, and your standard. What is the probability of obtaining a mean of 58 and less? So suppose you draw 23 samples from a population with a mean of 11 and standard deviation of 5.8. What is the probability of obtaining a mean of 13 or more. Suppose you draw 35 samples from population with the mean of 78 and the standard deviation 7.9. What mean to 61.78% of the sample means 4 above. So you can see the keyword above here. Suppose you draw 28 samples from population with a mean of 103 and the standard deviation of 10.5. What range of means covers the middle 1.33% of means? So you can attempt these ones, then you can look at the solution in a few minutes to come after your time. So in 5 seconds you can pause. 5, 4, 3, 2, 1, pause. I guess you've taken your time to solve these ones, so please do these practice questions. It will measure whether you are getting what we are discussing with you on these lectures. So please do some review practice questions so that we can make those concepts sink in deep. So let's look at the solutions. So for practice question 13, you know your new standard deviation, and what we need is mean is less than 58. So you calculate your standard error, then you get this value, then your z-score is equal to mu minus 1, then you see 58 minus 63 divided by your standard error, get this one here. So you go to your z-tables. You go to your z-tables, you're supposed to get something like 0.79. So this is your answer. For question 13, your mean and your standard deviation, you want the means that are greater than 13.4. So first calculate your standard error. So this is your standard error. The formula, remember this one. Then you input, you're supposed to get this one. Then you put your set value, then you subtract it, indicate your set value. So from the tables you go, then you input your set values. So you're supposed to get a proportion of 0.0236. So question 15, your mean, center 9, your standard deviation 7.9, then you are required to find means which are greater than, probability that the mean is greater than. So if you go back to question 15, suppose you draw 35 samples from a population with mean 79 and the standard deviation 7.9. For what mean to 61% of the sample means 4 above. So now, which means we want it to be above 61%. So when we're talking about above, remember, so the Z value from your tables, it gives you this one. The position of this one. So we want above. So we want above. So now when you go to your Z tables, you see that this value corresponds to the proportion of this one. So remember, the table is like this. Just put proportions here, and your Z values are here. And you change here the Z values. So what you do, you look for the proportion of 61. Then you project it to your Z value. And you just make that. So I do. If you have any problems in solving it, you can contact me and I will surely assist you. Given new this one and your proportion of this one. So the area in each tail is 1 minus . So remember deviation. So now, for the area initial is supposed, remember, you only want the middle part on this one, see? We don't want it. Because remember, your question is clearly that which is between those two, the range. It means one this range. So for the first one, you can know that this area and this area, they are equal. This is 49.0.49335. This one 3.4. These two are equal. Let's call it x. These two are equal. So for you to be able to determine 0.49, it means, remember, your tables, they give from the right. So it means for you to get this one, you're supposed to, so to get the z value for this one, it means, remember, you look for 0.49335. So for you to get this one, because this one is equal to 0.4. So now the z value here, you determine using this one. But this one now, because your graph, remember, it's given this shaded area. So it means for you to get the z value for this one, it means to subtract. So it becomes 1 minus 0.49335. In order for you to get this one from this one to there, so that, because this is just to determine this z value. So once you get this z value, you're able to determine the x using the formula, the x bar using this formula. X bar divided by square root of n. So I think it's good and cool. But anyway, it's the same thing, but only that, remember, these things are proportional. So once you determine the first z value, it means the other one will be a plus. So that's one, you see. That's what we demonstrated on that one when we're looking for 0.025 and 0.975. It's the same. It's the only difference is that z value on the side will be positive and the z value on this one will be negative. Because remember, the graph is like this, and the middle number is 0, so it's mean of, so all numbers inside will be positive, all numbers is this. But remember, they are symmetrical. When here we want 2.5% from the right extreme, which means that 2.5% on the left extreme will be having the same z value, but the only difference is that the other one is positive and the other one is negative. So for this kind of problems, we will specifically give you some exam tactics to save your time in the exam section, section 7, I mean. So make sure that you also are able to view those exam tips, because in this section we are only showing you how to solve it. But now on the exam prep section, what we will be doing is to solve them quickly or saving your time, so that you won't waste your time doing some of the stages that we to just take away your time that you could otherwise have used on other questions. So let's move on. Thank you for watching. If you have any questions concerning this section or you need any further information, call us on 074 920 9697. Thank you and have a good day.